there's still a few more topics we need to cover before we can really start looking at some circuit components and some actual applications of these components here. So we really still have a little bit more to go. So we're going to now talk about voltage division and do an example with this. Now, voltage division, this deals with a series circuit. That's what we have to do with. It deals with a series circuit here. And let's go ahead and see the formula for voltage division. And it's actually going to be a pretty straightforward formula for us. So we want to find V3 in this here. Now, this is a series circuit, so one thing we've talked about in the other videos is that one thing we know about a series circuit is that the current through all the components is the same. And specifically one we want to find here is the voltage 3. Now, if we found I, we know V3 is simply going to be I times R3 if we found the current. Well, the nice thing here is the current, remember for a series circuit, we have that voltage is equal to current times my equivalent resistance for a series circuit. And so we also then know, here I'll switch back to back, that for a series circuit, to get R equivalent, we would simply add up those resistances. So in other words, what we can get here is that we can solve this for I then, which means that I is equal to the power supply voltage, V here, this is the power supply voltage, divided by R equivalent. Which then gives me that the voltage 3 is going to be the current, which is voltage over R equivalent times R3. Now, we typically write this in terms of the resistors being divided, so R3 over R equivalent times my power supply voltage. Now, if we think about this some more here, we could clearly see that if in this circuit I was looking for V1, you can probably guess what it would be. It's going to be R1 over R equivalent times V, and V2 is going to be R2 over R equivalent times my voltage source. So this gets me, this is called voltage division. And so voltage division here and I'm going to emphasize here, series only. We only apply voltage division when we have a series circuit or two components in series. We can, it doesn't, the whole circuit doesn't have to be in series, but the components you're looking at have to be in series in order to do voltage division. And so basically what we have here is I'll put V sub n, because that's whatever resistor we're looking for, is equal to R sub n over R equivalent times the voltage supply. And that's it. So let's look at a quick example here. Okay, so we're going to find the voltage drop across each resistor using voltage division. So there's really not much to going on here. First we find R equivalent, which is, of course, 3 plus 2 plus 5, which is 10 ohms because we're in series. And then we simply go ahead and find all those voltages. So V for the 3 ohm would simply be, well, it's 3 ohms divided by the R equivalent, which is 10, times 15. And so we do that, we get 4.5 volts. And then we just continue on doing the same thing. Volts across the 2 ohm, 2 ohm divided by 10 ohm times 15. And we get that this is 3 volts. Now, the voltage drop across the 5 ohm resistor is 5 ohms over 10 ohms times 15, which would be 7.5 volts. So that's it. That's voltage division. Now, one thing we should notice here, if I were to sum up these voltages, 4.5 plus 3 plus 7.5, we get back to 15 volts. This should not surprise us at all, because KVL, if we were to draw this here, we know that the sum of all the voltages in this loop has to equal 0, or another way to think about it is this 15 volt supply has to deliver 15 volts in total to the circuit, so there's got to be the sum of these voltage drops has to be 15. There's one other thing we should take away from this here, and it can help you sometimes so you don't make a silly mistake on a problem here, is the larger the resistor, the larger the voltage drop. Now this should not be surprising at all, just looking at the formula here. If I scroll back up to this formula here, the larger the resistor, and if I'm saying the larger the resistor, I'm increasing R sub n. So if I'm increasing R sub n, well then of course V sub n is going to be bigger. So the larger the resistor, the larger the voltage drop. And we can see that again here. The largest resistor was 5 ohms, it had the largest voltage drop. The smallest resistor was 2 ohms, and it had the smallest voltage drop across it. All right. So let's look at one more quick example of this. So we're going to find V out here uses voltage division. Now, this is what gets people sometimes, I think, with this problem. They're like, well, how could I do voltage division on this? This is not a series circuit. It's not purely series, it's not purely parallel. And the temptation might be to try and put this in combination form, but this is where you want to kind of think sometimes not just of simple circuit elements, but of blocks. Because if I put a box around both this 3 ohm and 6 ohm resistor. So basically I'm putting a box around them. This box then has 2 terminals. It's got a terminal right here, and it's got a terminal down here. So the voltage supply is in parallel with the 5 ohm resistor and the box. You might say, oh, big deal, it's in parallel with that. But that is a big deal, because then we know that the voltage across each of these things, because it's in parallel, is the same. So there's 18 volts across that 5 ohm resistor, but I'm going to emphasize it's across this entire box. There's also 18 volts across the box. So what I can do is I can just examine this 3 ohm and 6 ohm resistor. There's a terminal here and a terminal here. And now that's what's, quote, inside my box. And there is 18 volts dropped across both of those resistors. Now these resistors are absolutely in series. So V out is going to simply be my 6 ohm over R equivalent. And it's just the R equivalent of these two resistors, because that's what is inside the box, times, well, what's the voltage supply? Well, we know the voltage drop across the box is 18. And of course, R equivalent in this case is 3 plus 6, which is 9 ohms. So V out is 6 ohms divided by 9 ohms times 18, which gets us 12 volts. Now again, we're using voltage division, but the original circuit, we weren't able to apply the original voltage division to the original circuit. We had to kind of think about it here as that, well, if I drew that blue box around it like I did, then the box, the 5 ohm, and the power supply are all in parallel. So then I know the voltages across all of those elements. And then I can simply treat what's inside the box as a series circuit, because they're absolutely in series, and just do voltage division from there.